right. We are back with another episode in the series of Leetcoding until I'm a Leetcode god. Part 11. I had to take a few days off from streaming, mainly because I just had some things that came up in my life I had to take care of. Probably like 2 of those 5 days I was gone, I just decided to take a break. I didn't even do much Leetcoding during that time. I started Leetcoding again yesterday. So I didn't stream yesterday, but I did like Leetcode. So I finished up binary search trees. What else do I have to do? Yes, I finished up binary search trees. I haven't done the hards. My plan is to go back once I finish all the mediums in the Leetcode 150. I'm gonna go back and then do the hards. Like, I'm gonna go back through, review all the problems, and then just do like the hards very quickly. Because it's not gonna take me that long to do the problems now that I've seen all of them again. All of them before. I'm also eating these pancakes from Trader Joe's. They're like griddle pancakes. They are so good, bro. Straight fire. But I don't know. I think to warm up, I go back, do some of the tree questions I struggled with yesterday. I think I'm just gonna do tries real quick, just to get it out the way. I think I'm gonna go to backtracking. I think I'm gonna do backtracking. Since it comes up so, like, I think backtracking, you're gonna have to use it for dynamic programming. I think you also use it in some stat questions, to be honest. Gotta drink more water, guys. Alright. Now that I ate, I have to text someone back real quick. And I will be ready to get going. Sometimes I wonder if, like, I have my damn. I wonder if I have my mic too far. But I think the audio seems pretty fine. I'm not somebody that talks very loud. So I should do redo some of the tree questions. Which ones did I struggle with yesterday? Lowest common ancestor. Let's do it. I'm really trying to make Leetcode. I'm sorry. I feel like I had something in my throat. But I'm really trying to make Leetcode a consistent part of like my day. Even when I'm busy. Eventually, when I get a full-time job, I want to incorporate Leetcode into my daily routine. Even if it's just doing like one problem, I think it goes a long way. So, binary search tree, lowest common ancestor. Yeah, so yeah, so I know for this question, what we are going to have to do is lowest common ancestor. Well, I can think of like the main cases that we're gonna have when we're dealing with this problem is if like both P and Q, right? So P is 2, Q is 8. Both P and Q, if they are less than the root node, they're going to be on the left side of the left subtree. If they're greater than the root node, they're going to be on the right side of the subtree. And then if they are neither of those cases, then we have like a lowest common ancestor. You know what I mean? You can just return the root. So I think the first the first thing I'm gonna do is check if P is less than the root and Q root. And we're just gonna return like we're gonna make a recursive call onto like the left subtree. So lowest common ancestor with root left P Q, right? And then we can just basically do the same thing. Like that. Just do root dot right. And then I think the only the only other case I'm gonna have to return the root, right? I think this is dot val. Let's look at the value, not just the node. root dot val. I need to start timing myself to, get a sense of how long. Yeah, they get a sense of how long these problems take me. Okay, so it's not. It's the fourth. Most common ancestor binary tree. This is my 5th time doing that question. I'm gonna make tree questions I've just been doing. Medium. Okay. What did I do? Count good nodes. Oh my goodness. I swear, I have like the biggest desire. Like, I would like nothing more than to just play FIFA pro clubs and just grind on that. I started playing it a little bit, after I finished all my work. I would hop on at like midnight, play with my friends. And it's like, bro, there's nothing more than, I would want nothing more than just to play that right now. That's really what I want to do. But I know I just have to finish my work first. I have to do this, and then I have to work on my thesis. That's another reason I wasn't really streaming, because I had to prioritize, getting a lot of my thesis done, which I'm still kind of slacking on, to be honest. I don't know why. It's just hard for me to just really work on it. I'm just typing up the report, and I find that so boring. All right. What's the problem? Count good nodes in binary tree. Yeah, so for this question, given about node X is in the tree. X in the tree is named good if the path from root to X. If in the path from root to X there are no nodes with a value greater than X, then the number of good nodes in the binary tree. So right, like 3. This one. This is 1, like, because you can't have anything less than. Oh, can't have a value greater than X. So 3, 1, 3. Okay. Yeah. So I think, honestly, all we have to do is just basically implement a DFS, and then we have to track the we have to track to see if there's been a number greater than the node we're at, like greater than like the node we're looking at, right? Like let me try and implement it. I know I'm just gonna start by implementing a just DFS, and it's crazy because I used to do a little bit more work with binary search trees because I'm good at implementing them iteratively, 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 iteratively. But when it comes to doing it like recursively, I'm not the greatest at it. Like I don't really feel confident. So I'm hoping that's something I can just work on. Okay. We're gonna do well stack for I in range length stack. But I remember, okay, so we can't just have the root. We have to have the root along with minus infinity. Yeah. Because this is gonna keep track of like the largest value we're gonna have. And we're also gonna need like a count value. Oh my goodness. All right, if I'm gonna check if max is greater than or equal to node val, then we're going to I'm pretty sure we're just gonna increment the count. We're gonna have max equal max of max value and node dot val. Then if Return the count. I think this is it. I guess maybe we should start it actually at 1, since we know that the root node is already. Yeah. Yeah, because and this works because basically all we're doing, it's like a normal DFS, except we're keeping track of the max along this path. So anytime we find a node that's bigger than the node like we're looking at, we can just increase our count value. Yeah, so like we get here, because like along this path, right? 3. This is gonna be our max value. Then we're gonna look at 1. That's not bigger. This it's not bigger. Okay. Then we're gonna look at like here. I'm gonna mark it because 4 is bigger. I'm gonna mark this one because 5 is bigger. Yeah. Yeah. Should work. That's a minute. But maybe it doesn't work. Dang, what did I do wrong? Hmm. Look at what it did. Oh my gosh, I'm not popping the. Oh my goodness, bro. I forgot we're doing DFS. I have to pop the last. Okay. That's embarrassing. Embarrassing. I'm gonna just say that I got that though. I'm gonna be real. The logic was there. I made what? Bro. Okay, now I need to do this one again. Yeah, I need to do this one again. Validate. Yeah, third time I do this. Okay. Right subtree if node contains only else is great. Key is greater than the node's key. Okay, I'm pretty sure for this question, I don't remember how to do it. Because we can't just look at if this is less than this, right? Like if this node is less than the root node, and then this node is greater than the root node. You can't just go through and check that, because there's going to be cases where, like this node could be bigger than this node. You have to actually like understand the structure. I think this question, damn, what? How did I do this? I remember the solution wasn't even that bad. I don't even remember the approach, bro. Remember if I had to do some sort of traversal? I don't think so. do in order traversal. Okay, so I know like with a binary search tree, if you do like the in order traversal, it should be strictly like increasing, right? And in order traversal is basically where we do like the left, the root, and then the right. I'm gonna look at this. Oh my goodness, bro. Oh my gosh. I remember now. I remember now. I remember how to do this. Because, okay. Basically, what you have to do is you have to remember that, like, for each. When you go down, like, each side, right? If you go into, like, the left subtree, the max, like, the max that any node on this subtree can be is 5. Like, is the root node right here. 5. Um, Same thing with here. Like the min that any node can be is 5. And it's the same thing here. Now like the min that any node can be is like 4. On like yeah. Yeah, they all have to be greater than 4. Man. Oh my goodness, bro. It's crazy, bro. Oh my gosh. Let me try and implement it. I'm gonna have to come back to this question, but I think I remember how now, like just with that knowledge. And am I implementing a stack, or I think I'm doing DFS? It's just me checking if it okay. It's a stack, yeah. Well, let me just practice doing this again. Let me see. I'm sorry. Not gonna lie, I just saw the news that Kristaps Porzingis is returning for game one of the finals. I think I expected that, but it's great seeing it um, actually be announced. I don't expect him to play that many minutes, but still great having him there. It's raining. Yeah, okay, so we're gonna check this. And then we're gonna check if we're going to check if the left node are we gonna check the if node dot left is greater. Okay, okay. Yeah, if node dot left is greater than the greater than or equal to, because I don't think it can be equal either. Yeah, if greater than or equal to um the upper bound. And I think we're just gonna return false. And we're gonna do the same thing for I feel like this is gonna give me an error though, because what if it's null? We're just gonna stack dot append. We're going to append um node dot left. It's gonna be the root now. This might be no.val. I don't know. It should be right. Because the lower bound should be upper bound should be this. And then I think if we go through all this, we can just return true. Yeah, that's what I thought I would get. Okay, it has to be no.val. Does that make sense? Hold on. Now I'm confused because if the node then so we're just checking to see if it's like in the bounds. Okay. Yes, I think this is going to be a question I do over. Dang, I feel like I'm not even going to be able to do case mouse element. Oh my god, my eyes. I have allergies. And it makes my eyes itchy. Oh dang. I cannot play music. Mm. Bro, Chris Las Vegas is so good, man. Like, all right. So this question, K smallest element in a binary search tree. This one I think is pretty straightforward. Like, all we're gonna do is look at like the in order traversal, right? I'm pretty sure we're gonna need to. Like here, I think what I need to do. I need to look at the left node, right? Um, if root dot left. And check if self dot count equals k, and all we're gonna do is We want to return the node or the value? Value. Right, and then now we're just going to look at the right node. I don't know. I think we should be returning. Output 2, expected 1. I don't think this is gonna work though. But I feel like I did it right. Because we're doing root.left, node, equal root.val. We're gonna increment the count. Should we start count at 1 actually? I think we. Oh yeah, hold up. Wait. Oh, it's 1 index. That's, bro. I think that's the issue. Yeah, that's the issue. I did not read. I was starting at 0, and it should be 1. Okay, cool. I was like, damn, if I couldn't do that, I'm gonna have pretty big issues. Yeah, bro. So I'm also pretty into soccer, and it seems like, you know, I'm a big Mbappe fan. That's my goat. He's going to Real Madrid. I'm excited about what's next for his career. I'm expecting. I think his first season in Madrid, he'll probably have like 27 goals, maybe like 9, 10 assists. I feel like it's probably what he'll have. I think for sure he'll get so we even need to check if there is left. Okay. What's the next thing? Construct binary tree from. Man. Ew, I do not like how that looks. This is gonna be our second time, right? I also need to give my dog a bath. He smells so bad. This one, I feel like it's. When I tried to do this question for the first time, I genuinely felt like it was impossible. After looking at the solution and kind of like watching a few videos, it makes a lot more sense to me, but Okay. Construct binary tree from pre-order and end order traversal. And just to explain a bit about like pre-order traversal, that's basically where we do the root node and then we do the left and the right nodes. In order is basically when we do left, root, right. Post order is where we do left, right, and then root. Level order is basically just a breadth first search. I know, like, first step is to this writing down, like commenting what I'm doing helps me with problems that are a little bit more difficult, you know? Like with this question, I know we need to get the index right from, we get index of root from in order list, right? And then the way we could do that, we could just have like index equal in order it should be the first, right? Yeah. Then basically, what do I want to do? Then we can just do like root equal equals tree node of val equals what? In order index. And then basically we want to build the left and right trees. So we can do like root dot left is going to equal oh, I think we actually just want to pop because we don't just want to, like, you want to get rid of that. Then with the left, I want to just do. Oh my gosh, there's like 2 ants on my bed. I gotta kill this. Gotta kill it, bro. Bro. I'll be right back. Okay, yeah. I don't know if I killed the ant. Because I could not find its, like, I don't want to say carcass, but you know what I mean. So, the left is just going to be from 0 to index. Right? And then the right node is going to be I want to go to like the next index all the way to, yeah, I think it's to the end. I think after that we could just return root. Because we're supposed to return, yeah, a tree node. Alright, let's see. Oh. Should we actually make the right and left ones? Or should we? Is it dot index or is it dot get index? Yeah. Pre-order dot pop. I feel like this should work. What am I doing wrong? Because hold up, yeah, we're building out the left side. Pre-order dot pop. We're popping the first element. Index. We're trying to get the index of let me see what I did. Okay. Bro, is this not what I just did? In order index. What did I do? Pre-order dot pop. Yeah. In order dot index. Pre-order dot pop. Bro, this is exactly what I'm doing. Am I just slicing wrong? Oh, it's not a build tree. Oh, you gotta just do if. I forgot this statement. We can only do this if, like, while we have a list in order. So that's probably what's happening. It's probably going through and we don't even have the in order list because it's empty. That makes sense. That's probably what's happening. Am I returning? Oh, this has to be. Oh my god. Like, damn, bro. It's rough. Yeah, well, we're gonna need to do this question again. So what are we doing now? "13 binary tree questions." Let's do tries, I guess. Pretty sure I've done this question already. I don't remember what a try is, though. Also, what the hell, bro? Backtracking just seems so, ugh. I do not look for it. This topic seems so confusing. I don't even really want to do it, but alas, here we are. Yeah, see, I already did it. Yeah.
I'm going to bring out the curtain.
All right.
All right.
Okay. Look at tries. Oh my goodness.
Hey, have you noticed that if you write something in Google, it automatically suggests you what you might be looking for? Well, this thing, among with others, is based on tries. Try is a tree-like data structure, so it has something called root, which is at the top. Yes, in informatics, roots are at the top. Also, every node can have something called child. Child is the node directly under its parent, and child node can also have childs. For example, the first node and second row have two childs, And if node have no child, it's called leaf. Now, let me show you how these nodes look like inside. Every node have references to its child. And since every node represents some character and prefix, to match the node with character, we will use something called map. If you don't know what that is, imagine that you have table and each record contains character and corresponding node. Also, since the is word, but also can be prefix to there, we have to be able to decide whether this word is in our tree or whether it is just a prefix. That is why we have Boolean variable which indicates that. Let me show you how we can add words. I got here my root node and words I want to add. So, let's add car. As I said before, every node represents one character of some prefix. So we split this word into characters and add to our tree prefix for every word starting with C. Inside this node, we want to add node that represents all words starting with CA. So we add A into its map and create a new node. So this new node represents prefix CA. As you probably figured out, we add to its map R character and create a new node. This node represents all words starting with car. Since we want to add this word, we set its indicator to true. Let's try to add Donna. So, once again, we start at root and look at its table and see that we don't have any node representing the prefix. So we create one and add new record to root map. In this new node, we look for O. Since there is no O in our table, we add it and create a new node which represents do prefix. In this node, we continue with N, where the same thing happened as we create new node for done prefix. In this node, we add E and once again create new node. And since we have no other characters in done, we set this node's word indicator to true, and we are done. Let's try to add try. Once again, we look at root and try to find T in its map, but T isn't there. So we create new record for T and add to it corresponding node. We move to this node and continue with next character, in this case R. Since this node map is empty, we add there R and create new node representing GR prefix. And
I just feel like, bro, if I'm asked this question,
Y record. And once again, we create corresponding new node. This node represents prefix try, and since this is the word we want to add, we set its word indicator to true. Now, let's add get to our tree. So we look at root, but we find out that C is already in our roots table. So we move to node representing C prefix. And in this node's table, we look for A. A is already there, so we move to corresponding node. In this case, we look for T, and we find out that T is not in our node. So we add T and create new node. And because we have no other characters in cat, we set the word indicator to true. Let's add try. We look at root's table and find out record T is already there. We continue with corresponding node. In this node, we find R and move to node representing TR prefix. Now we look at I in this node. Since it's not there, we create new record for I and new node for try prefix. Since we still have one character left, we create new record for E and new corresponding node. In this node, we set the is word indicator to true. Let's add our last word, D. We look at root and see that D is already in the table, so we follow its pointer. Now we try to find O in this node. O is in this node, so once again we follow its pointer. Since we have no other characters to follow, we set the is word indicator of this node to true. Let's try to find some words. First word is CA. Remember, each node represents prefix, so we start at root and look for prefix C. We follow C's pointer, and in this node's table, we are trying to find A, because in order to find CA, we need to find CA prefix. A is in table, So we follow its pointer and get to node which represents CA prefix. So we look at its word indicator, and since it is false, this word is not in our tree, even though we found corresponding prefix. Let's try to find zebra. So we look at roots table and look for prefix. This prefix. Follow its point. We need to find CA.
Why would that come up as false?
A is in table, so we follow its pointer and get to node which represents CA prefix. So we look at its word indicator, and since it is false, this word is not in our tree, even though we found corresponding prefix. Let's try to find zebra. So we look at roots table and look for Z. Since Z is not in there is no way that zebra is in this tree. Actually, because Z is not in root, we can say that any word starting with Z is not in this tree. Let's find try. In this roots table, we found T record, so we follow its pointer. In this node, we continue with R. Since R is in this node's table, we follow its pointer and get to node which represents TR prefix. In this node, we look for last character I. I is in this table, so we follow its pointer. And since we have no other characters left in our word, we look at this node's is word indicator. Since it is true, we can say that tribe is in this tree. Let's try to find card. We start at root and follow C. Then we follow A. We still have 2 characters to go, so we continue with R. We get to node which represents card prefix and look for D in its table. Since it is not there, card is not in this tree.
Embarrassment. We're doing a fit. No. Oh, no. Going high. Oh, you got a real sweaty palm there, buddy.
Old Spice Genuine Super Hydration Body Wash with 24/7 moisturization and vitamin B3.
That means it hasn't been inserted yet, so what are we going to do? We're going to create a prefix.
I don't see how common.
Tree. So a trie or a prefix tree is a special type of tree, and it's used to efficiently store strings, and the applications are some stuff like autocomplete and spell checker. The reason is because the prefix tree allows you to efficiently filter and search based on prefixes. So let's look at the actual implementation of it. So we're going to have a object, that's what we're going to be doing this time, a trie object. And our job is to fill in 3 functions. The first function is going to be inserting a word into the try. The second function is going to be searching for a word in the try to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the 3 functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a try actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the try, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just added it, so of course we're going to return true, apple exists. Then we're going to check, does the word app exist? It does not. The word app does not exist. And third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a try is. And in this problem, they told us that the limitation is that the words are going to only have characters from lowercase a to z, right? So this is lowercase a to z, so that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say a, insert it, p, insert it, second p, keep doing that, and every time we're inserting a new character, we're going to add it as a child of the previous character. So we inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP. But we know we actually did apple, right? Full on apple. This is the last character. So we mark here as the last character. We are marking it even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe. So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So potentially we could have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D. So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder node, right? It doesn't have any characters, but it's considered the root, right? And so we're going to check, does this root have the child of the first character that we're looking for, right? So take a look. This is the word we're looking for. Obviously, we're looking for the character A. So we check, hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next. character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right, as a child. So next character, P, does this have a child P? Yes, it does. Next character, L, we have a child L. Next character, E, this is the last character, so we do have an E over here, right? And last thing that we have to confirm is, okay, this is the last character, is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because apple does exist in the try. So next, let's run search again, and this time, let's check if a word app exists inside of our try. App, right? Not apple. So obviously we know that starting from the root again, we do have a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, a, p, p, shouldn't this function return true? No, we're not returning true, and the reason is this node is the last character of the word, right, p, and it's not marked blue, meaning it's not marked as a word, right? Remember, we only inserted apple into our try, right, into our tree, and we marked this as the end of the word. We never inserted app into the tree, so this is not marked as the end of the word. So we return false for saying that app does not exist in our tree. App is not a word yet. Next, let's run another function on our tree or try. We're going to check, does a word start with app? How can we check if a word starts with app? Well, we're basically running the exact same thing what we've done, right? We're starting at the root. We're going to check character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them. Start at A exists. Check P exists. Check another P does exist. So since we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right, we never inserted app, or we're guaranteed that there is some word below that has been marked, right, because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right? There definitely exists a word that starts with app, right? And so this starts with function is the main reason we're even implementing a try in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we can just use a hash map for that, right? Because hash maps or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? A-P-E. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say A-P-E and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child of A, this is a child of P. Are we going to do that? No, because we could reuse it, right? Why would we have duplicate A's in the first position when we already have an A over here? So if we are inserting this word ape, we're going to leverage this A that we already created. Great. And then we're adding the second character, P. We're going to leverage this P that we already created. And so we've inserted the first two characters. What about the last character, the E? Do we have an E over here? No, right? There's no E in the third position. So what are we going to do? We're going to create another child node, right? Now we create an E. And last but not least, we mark that this is the end of a word. So you can see that a try actually has the potential to be pretty efficient because we are reusing a lot of nodes, right? We're not necessarily creating a separate node for every single word. Now let me just show you one last thing before we jump into the code. So we're going to do one last function. We want to check, does any word start with B? And I'm just illustrating why we're even implementing a try in the first place. It's because the starts with function is very efficient compared to other data structures. So for example, let's say we had a list of words, a list of strings, and let's say the size of that list was equal to 1,000,000, right? How long would it take for us to check if any word starts with B? Worst case, we would have to check every single word in the list and check if it starts with B. And what if there was 0 words that started with B? Then every time we would have to go through that entire list of 1,000,000 words. But with a try, like we've implemented right now, it's very efficient. Here you can see we have 2 words, right? We have one word here and we have a second word here, and it's possible we could have 1,000,000 other words, right? Like clearly, there's probably a lot of words that start with the character A and maybe so on. But when we run this function starts with B, all we're checking is we're starting at the root. We're checking, do we have any children with the character B, right? We check this first layer. How large is that first layer going to be? Well, we know that there's 26 lowercase letters, right? So worst case, it would be lowercase 26. And that's pretty efficient, right? So when we check, hey, there's a lowercase a, but there's no lowercase b. So for this starts with function, we can return false. And that was done very efficiently, right? 26 is basically big O of 1. So this is a super efficient way to check prefixes, right? And that's why they call this a prefix tree. Prefixes can be checked very efficiently. So now let's actually jump into the code. All three of the functions, insert, search, and starts with, are pretty similar functions. So even though we're going to write a lot of code, it's going to be mostly similar. So let's jump into that. So our job is to implement a try, but we can't really do that without implementing a try node. So the first thing I'm going to do is create a try node, and all we're going to do is just create the constructor. So in Python, that's what I'm doing, and net is basically the constructor. And I'm just going to have a couple of member variables for this. So we are going to have children of a try node, right? It can have children. It could have 26 children, but instead of doing an array, I'm just going to do a hash map because that's easier. And remember, we can also mark every single node as if it was the end of a word. I'm going to say end of word is going to be a variable. Initially, it's going to be false, but we could set it to true if the character was the end of a word. Notice how we're not actually storing the character itself in the try node. That's going to be implicit from the hash map, from this hash map. So if we were adding let's say a character a lowercase character a, we would say to children, children, for character a is the key, and we're going to create a new try node for that character a, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire try node class. Now let's actually get into the try type. That's how we're going to, and we're adding let's say a character a lowercase character a, we would say to children, children, for character a is the key, and we're going to create a new try node for that character a, right? So that's how we're going to be doing it. That's how we're going to be inserting a node. So that's our entire try node class. Now let's actually get into the try class. So the first thing we're going to do is initialize this. So let's get rid of this comment, and for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root try node, and that's it. That's all we're going to do for the constructor. And once the try node is created, we basically have an empty tree. Even though we have a root, it's empty because it does not have any children. So we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize ourselves. Current is going to be set to the root, so we're going to initially start at the root, right? And then we're going to go character by character in the word. And for every single character, we're just going to check two things. Does this character already exist? If it doesn't already exist, so if this character is not in the current nodes dot children hash map, right? So if this character is not in our hash map yet, that means it hasn't been inserted yet. So what are we going to do? We're going to create a try node for this character. So cur.children, and the key value we're going to use is the character, and then we're going to create a new try node. So this is how we are going to be inserting characters. To children, we're going to use the character as a key value, and then we're going to create a empty try node. And we're only doing that if the character doesn't already exist. If it does already exist, then we can skip that step and just say that current is going to be set to that child, right? So if that character already existed, then we can just update cur and move to that character and then continue our for loop, right? So we're going to do this for every character in the word, and then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something, the characters already exist, or we just created them. Now current is set to the last character of the word. So what are we going to do to current? Well, we're going to mark it as the end of a word. So we're going to set end of word equal to true now, and then we don't really have to return anything. So that was pretty simple, right? Not a lot of complex code. We did have to go through every character, and we either created nodes or just iterated through those nodes. And and the remaining two functions, search and starts with, are actually going to be very similar to this insert function. So now let's get started on search. So we want to search to determine if a word exists or not. So just like the previous function, we're going to start at the root node, so self.root, and we're going to go character by character in the word, and we're going to check if this character exists in our tree. If it does not, so if C not in current.children, if this character does not exist, then what do we have to do? We return false, meaning the word just simply does not exist. If it does, then we can move ourselves to that child node. So we can update cur and set it to the child node of that character. And then we're going to basically keep doing this for every character. Character in the word. If the word doesn't exist, we'll return false. If the word does exist, that means the entire loop will execute, and then then cur will be the last character of the word, and we know that it is a word if cur has the end of word variable set to true. So this is the variable we're going to be returning. If this is set to true, that means this is a word and will return true. If it's set to false, that means it's not a word and our function is ultimately going to return false. And now, last but not least, let's get started with the starts with function. And this function is actually going to be the exact same as the search function, except we're not going to have to determine if it's the end of a word or not, right? We're not checking if it is a word, we are just given a prefix, and we just want to know if there's any word that starts with this prefix. So once again, for the third time, we're going to be starting at the root, and we're going to go character by character in the prefix this time, right? We're not given a word this time. And if this character is not in our tree, so if it's not in the children right now, then we will return false, meaning the prefix does not exist, therefore no words start with this prefix. Otherwise, we will shift our current pointer to that child pointer of this character.
I want to check out a different solution.
At Amica Insurance, we look out for you, so you can look out for them.
For each letter inside the word, same exact thing. But if instead of creating a new tree, basically tree is a tree-like structure where usually you'll store strings inside, and it's very similar to a binary tree where we have a root, and this root has children, and those children have more children nodes, and so on and so forth. For this particular example, we're storing a string, and each level of nodes represents the letter inside of the word. So level 1 represents the first letter, level 2 represents the second letter, and you can see that here with the word 2, we have T here and O here, T-O, and with like the letter T, it's like T, we have E here and A here. And basically you can use structures like this to save space, because we don't need to store the repeating letters. We already know we have a T for this letter. So how do we implement this? Well, we want to be able to do an insert, we want to be able to do a search, which means this exact word exists inside the tree, or we want to do a starts with, which means, well, these beginning letters are somewhere inside this tree. It doesn't necessarily need to be the word though. Okay, so the way I solved this was first initialize a node class, very similar to when you use like a linked list or a binary tree. I want to initialize a node here because it's easier for illustrative purposes and more similar to how a linked list or a tree works. You could use just a dictionary to do this, but for this I thought this is fine. So let's see, what do we want to store within the node? Well, we just need the children, right? We need a dictionary that says these are the children that this node points to. So that's it. As far as when we start with initializing this tree, we always need a root, right? Just like a binary tree, we're going to start with a root, and that's just going to be a node that we initialize. So simple enough. Now when we do an insert, this is where it starts getting a little tricky. We have to insert each letter sequentially. And we're going to traverse down this tree structure just like a binary tree at each level down. And when we do an insert, basically if this letter doesn't exist inside the child, we need to create a node for that letter, and we'll build it while we're going down the tree. So let me just write it down here. Let's first start with like a pointer. We'll just call it pointer equals self.root. So for each letter in the word, we'll check. Okay, if letter not in pointer.children, we need to insert inside this dictionary, right? So pointer.children, letter, we'll just initialize a new node whenever we do that. Otherwise, we know that exists, so we can say, okay, this pointer is going to equal pointer.children, and whatever that letter points to. So each letter inside this children is going to point to a node. Okay, so we'll just continue down that loop until we finish, and once it finishes, then we have our letter inside this tree structure. So that would be it for the insert. There will be something else I need to add, but I'll show you first. What about like a search, right? Well, it's very similar. We first start with the root, and we're going to go letter for each letter.
Oh yeah, because we're initializing the root. That's not like a letter or anything. Okay.
Letter inside the word, same exact thing. But if instead of creating a new key inside the children, if it doesn't exist, if this path gets broken, we immediately return a false. We'll say, hey, this word doesn't exist, there's no path for it, so that's that. If it is able to get through the whole thing, then we can return a true. But we've reached a problem here, because what's the difference between search and starts with then? Because if you think about it, let's say we insert the word ABCD, and we search for ABC, technically that word doesn't exist, right? But given this logic, we'll return a true, and there's nothing to differentiate that with the starts with function. So how would we differentiate the two? Well, what if we mark the node to say this is the end of the letter? Like we'll say end of word, it's a Boolean, and whenever we do an insert, we'll mark that node, the last node, with this pointer here. We'll say whatever the pointer is going to be pointing to the last node when we do an insert, and we'll set it to true. And that way we can check when we do the search, hey, do we have this Boolean set? Because if it is, then it is the end of the word, and otherwise it's not, so we have to return a false. Yeah, so looks like I forgot something here. I have to move the pointer towards this. And at the very end, right, let's check end of word. We'll say if pointer end of word, then we can return true. Else, if it's not, then that doesn't count. It's not the end of the word, even though the path exists for it. We can't return true for that. But starts with is different, right? It's pretty much the same thing, but the difference is we don't need to check for the end of the word. As long as it gets through this entire loop, we could say, yeah, that counts. Okay, it does exist. This path exists. The start with exists. And I think I need to change this to a prefix. So that should be it. Let me do submit. And let's see, null, null, false, null, null, true, false, true, true, false, true, null, true. Let's submit that. Accepted, good. So like I said before, technically you don't need this node class. You could just use a dictionary at the root here and do like a nested dictionary where each dictionary value is another dictionary at different levels, and you could just traverse through this dictionary inside here doing that, but it was kind of hard to illustrate that, so I thought this was easier, and that's how I solved it. So thank you.
Yeah. Marciano. Yeah, I'm not. Wait, the guy who knows. Yeah.
Okay.
So I moved out,
I mean,
and then we ended up.
that makes sense. So like, I'm just gonna try and go based off my understanding. So yeah, we're just going to be creating a new node. How else we're going to go to there. Then, I mean, we're going to keep doing this, and then eventually we're going to get to the end. We're going to have point. Let's do self. Does this self dot point dot description?
Point to a node.
I feel like this is all I have to do.
Okay. Third, we'll mark that node, the last node, with this pointer here. We'll say whatever. Wait, we could just the end of the world.
Okay, yeah.
Pointer, or-
I'm right. Okay. Then what do I have to do for the search? Basically checking this. we're gonna just return false because but then what do we do with the end of word in the search?
This. And at the very end, right, let's check end of word. We'll say if pointer end of word, then we can return true. Else, if it's not, then that doesn't count. It's not the end of the word, even though the path exists for it.
Okay. I think this is exactly just like the same thing. Bro, who was texting me? So it's pretty much the same thing. I think we just don't care if it ends with it, right? Well, if C not in... Oh, we're just checking the prefix. So actually, yeah, so if we get through... then I think we just want to return true. Oh.
true for that. But as it gets through this entire loop, we could say, yeah, that counts. Okay, it does exist. This path exists. The start with exists. And I think I need to change this to prefix. So that should be it. Let me,
Cause wait, what? What am I doing wrong? When did I do this question? I did this question in 2022. Damn. I totally missed the I don't think this even matter, bro. Damn, so you really have to do that. I think because, yeah, because I think I would actually be changing. Any reason you're doing Leetcode instead of projects? I'm mainly doing Leetcode because I'm not good at it. I had a few like interviews earlier in the year, and I completely bombed them, honestly. Like, I don't even think they weren't even asking me anything crazy, and it was for like an internship. I just couldn't. I was so bad at them. And I'm still working on projects. I'm currently like finishing up my master's thesis. Want to do elite rooms with Discord? Uh, I'll be down. I mean, currently just like leak coding when I can, so I don't know when I would be on. Oh, they have time limits. I'd be down, honestly. I'm just going through the Leetcode 150 right now. Like, I'm still a pretty big beginner at Leetcode, but I think anything to get a bit of experience, I'm down for. Wow, I actually have 2 views. Yeah, but I've just been working on my master's thesis and Leetcoding in my free time so that I can actually, have a chance in interviews. But definitely be down to do Leet rooms. I haven't heard of them. Yeah, so this question right now is just implementing a try. So I've just been going over. I've gone through all of these different topics. I just went through trees. Now I'm going to tries. So looking at implementing like prefix tree. basically have to initialize the try object, make like an insert, search, and starts with method. So a lot of the stream, I was just watching videos about implementing prefix trees. Yeah. It's honestly pretty like simple once you get the hang of it. I think just understanding the data structure, and basically it's just like nested dictionaries. I think it's pretty straightforward. So, and I also keep like just a spreadsheet of all of the problems I do. Even if I do like the same problems again and again, I just write down like what problems I did each day. So, because I think repetition is one of the most important things, you know. How long have I been streaming? 2.5 hours. Yeah, amateur coder. I stream pretty much like every day or so. I try to do it multiple times a week. Sometimes I just like practice without actually streaming. Yeah, thank you. I really appreciate it, man. People leaving comments, it motivates me to keep doing this, you know. I'm trying to be consistent over everything. I'm not trying to be the best immediately, but I want to get to a point where, you know, I'm not afraid. I don't have like anxiety going into interviews, because I think that's the biggest thing I have right now. Yeah. I don't want to do any more problems. I might stop here, honestly. I'm streaming for 2.5 hours. I have other stuff I have to do. But thank you for like hopping in the stream, leaving a few comments. I want to start making YouTube videos, talking about like a lot of different topics in AI. I got my master's in like artificial intelligence, so I'm mainly looking for like a data science ML job of some type, but a lot of them you need like PhDs, honestly. So I'm working on like building up my portfolio a bit. Yeah, but I want to make just YouTube videos talking about basic machine learning topics that I can, honestly, I'm doing everything kind of like for me. It's just easier to review when like you're just making a video, you know. You're kind of killing two birds with one stone. Make content for other people to watch, and it helps you remember, you know. So I definitely want to make a video about like what I did for my thesis. I want to make a video talking about different like ML topics. So maybe just going through like, you know, regression, SVM, I don't know, random forests, decision, like different trees and stuff like that. Talk about like transformer architectures. I want to do a series where like I talk about academic papers and kind of just break it down from like a high level. I think that would be very good. Yeah, so I have a lot of ideas for this channel, but I'm just pretty busy currently. So I'm hoping once I finish, you know, my thesis, write that up, present it. Hopefully I should be presenting it in like a week or two. I can just focus on making the YouTube videos and making a portfolio website. Let me see. Bro, I have this idea of like making a portfolio website with a React 3 Fiber. And I want it to be like bro, there was this 3D model I saw on Sketchfab. I'm a huge Dragon Ball fan, so. Just Dragon Ball. But basically, just picture like King Kai's place, and like picture like there was a better 3D model, but essentially my portfolio website, it would be like this, and then yeah, it'd be kind of like interactive. I kind of want to do something like that. I think it'd be really cool. And I don't really have a lot of developer experience, bro. I started out doing I went to school for like applied math for my undergrad, and then I worked at this health insurance company in Boston. I'm from Boston, and it was really just like an insurance like analyst, more so like just business role, and I didn't really enjoy it, so I went back to school to get my master's in like AI / applied computer science. I think it's like the program, it was titled like AI / applied computer science. And now I just finished that up. I still have a little bit of work I have to finish for that. But I've also been looking for jobs and stuff. I had a interview for like this ML internship. I thought I did pretty well. Got to the final round. Didn't end up getting it though. A little frustrating. I had a interview for a different internship back in like January. I didn't make it past the second round. I just bombed that interview. I had a interview scheduled for like a software engineering role. That's why I started this whole series. And that interview, they actually went to a hiring freeze. So my interview got canceled. It was pretty frustrating, but you know, just got to keep going. So I appreciate your comments, Amateur Coder and Everin Sen. Any reason you're doing Leetcode instead of projects? Man, because you got to do projects to get the interviews, but ultimately you got to do Leetcode to pass them. So I'm just trying to be consistent with doing Leetcode. Yeah, but I'm going to stop here. Go for a walk. But thanks for stopping by. I'll be on probably tomorrow morning.